It's my honor to present our work on lentiviral vector purification, focusing on the step of optimizing downstream chromatography. ABL has developed an industrial lentivirus LVV purification process, including a chromatography step using a strong anion exchange AEX column. So the graph here is the average result of AEX step from 3 of our 20-liter LVV production. Overall, we saw a good LVV recovery, TU P24 genomic titer, decent whole cell protein removal, but minimal whole cell DNA clearance. And also, in addition, across the industry, we have heard mixed feedback regarding the recovery of this column. So this is where our study initiated, is to understand the variability in lentivirus purification using this strong AEX. So so the LVV used here was produced at ABL in high density suspension cells, transfected at around 4e⁶ cells per ml, resulting high virus titer, along with the medium to high whole cell protein level in the chromatography load. However, lentivirus is often produced from the adherent cells or the low-density suspension cells, resulting low HCP and relatively lower LVV titer. So as illustrated on the right-hand side, this is what we think happened. The LVV bind very tightly to the strong AEX. So if the feed is too clean, look at the right-hand side, the LVV sticks and the recovery is low. Of course, if there's too much HCP, it competes for binding, resulting in the low recovery. Another point I want to make is amino acids are commonly used in the elution buffer during the purification of such as monoclonal antibody, AAV, etc. So people claim that they can improve the stability, recovery, or impurity clearance. Arginine is reported in the LVV purification. In our process, we use 1 molar sodium chloride. However, arginine may offer some advantages. So therefore, we hypothesize that for LVV purification, the column performance may be affected by at least 2 factors: the whole cell protein level in the load and your choice of elution buffer, such as arginine or sodium chloride. Our overall objective for this study is to optimize the performance of our strong AEX and also look for alternative columns with comparable or better performance and with broader or different range of HCP profiles. To do this, we aim to select a few columns, evaluate the impact of HCP levels in load, compare the sodium chloride versus arginine in the elution buffer, and then carry out panels of comparison to identify the top performers. So we evaluated 10 prepacked columns listed here from different vendors using our ActaPure system. Of course, number 1 is our strong AEX, and also inspired by the success of affinity resins used in MOB or AAV purification, we selected 4 of the heparin affinity column from 3 different vendors. So regarding the ion exchange column, we also selected 2-week AEX to CEX with heparin-like ligand. And also regarding the affinity column, we also selected a non-heparin affinity, which has not been launched to the market yet. So with this column in mind, we asked 2 questions. How well do they deal with different HCP levels? And how well can LVV be eluted from this column using sodium chloride or arginine? So we use frozen clarified harvest from 2 of the 20-liter productions as high and low HCP, high and medium HCP load, both generated from high-density suspension cell transfection. To model the low HCP conditions, we remove 80% of the HCP from one batch to mimic adherent or low-density suspension cell production. Our goal was to identify top performers with high recovery and strong impurity removal. From a CDMO perspective, we also prioritize fast and GMP-friendly process to reduce labor and human error while keeping the cost in mind for our clients. So the aim one of this study is to evaluate the impact of HCP levels in the load. As expected, our strong AEX performed much better in high versus low HCP. In several other experiments, it also did a good job with medium HCP. Regarding number 6 and number 8, the heparin affinity resins, they show an opposite trend. Both of them have very low recovery in the high and medium HCP. However, when we remove HCP using a mixed mode resin, the LVV recovery improves significantly. So, interestingly, the weak AEX, number 2, does well in all the HCP level tested, high, low, and medium. And regarding number 10, the non-heparin affinity resin, it behaves similarly to the other heparin affinity resins, which is it has a higher recovery in low versus high HCP. The only difference is it also performed well in the medium HCP. So the summary is illustrated in The summary is illustrated in this graph and the table on the left-hand side. So the dotted blue line is a strong AEX. It prefers medium to high HCP load. However, the weak AEX handles a broader range of HCP profiles. The heparin can only deal with the low HCP, but the non-heparin affinity resin can handle both low and medium HCP. I also want to point out that we also tried the number 4 CEX, but it failed with both high and low HCP, so we didn't do any further work. Aim 2 is to compare the sodium chloride versus arginine in elution buffer. Again, we started from the strong AEX, and in the step elution, as shown in the chromatogram and the bar graphs, arginine elution is more efficient than sodium chloride, with higher recovery and comparable HCP removal, but a minimal HCDNA clearance. In the following gradient elution, both arginine and the sodium chloride produce 2 peaks. The chromatogram here is the arginine shows the 2 peaks during the arginine elution. It's consistent with the step result. Arginine has a higher recovery than sodium chloride, but more importantly, majority of the LVV elute in the peak 2 of arginine with much lower impurity profile, so allowing the recovery of much cleaner LVV fraction. So this is very important news for us. Next, we evaluate the so next we examine the weak AEX number 2, and sodium chloride and arginine has showed comparable elution efficiency and a similar impurity removal. One good news though is both can efficiently remove the whole cell DNA. It's known that arginine is preferred over sodium chloride for the heparin resin, so we didn't show data here. So lastly, we evaluated the number 10 heparin affinity resin, and seems that sodium chloride is slightly more efficient. However, the sodium chloride / arginine elution provide better impurity removal. So the aim 3 is to identify top performers through the comparative analysis. First, we just summarize our finding about our strong AEX. It preferred medium to high HCP versus low HCP. Arginine elution is preferred over sodium chloride. So this column can effectively remove a significant amount of whole cell protein, but not much whole cell DNA. So it's compatible with the high density suspension cell culture. The heparin resins covers the opposite end of HCP load. So we did this is summary of the 4 heparin column comparison, and seems that number 7 has the highest LVV recovery. However, it doesn't remove any of the whole cell DNA. Number 8 is has a slightly lower recovery, but it removed a significant amount of whole cell DNA. So finally, we compared all the new resins using under the medium HCP and sodium chloride elution. Number 2, the weak AEX is a top performer with highest recovery in TU, genomic titer, and P24, as well as strong impurity removal, including whole cell DNA. Number 10, the non-heparin affinity resin is the second best performer. And also compared with other heparin resins, it runs at 10 times faster. So making it attractive for GMP scale-up by reducing time, cost, and human error. So this table summarizes the top performing resins under their optimal condition, with high LVV recovery and whole cell protein removal, but each has its pros and cons. Overall, the new columns showed a very promising performance as compared to the old ones of the similar type. The weak AEX is the best performer, but it's more expensive. Look at the cost. The non-heparin affinity resin, number 10, is second best performer, but it hasn't been commercialized, so with price unknown. Strong AEX, number 1, is much less expensive, but doesn't remove much of the whole cell DNA. The heparin are also cost effective, but they run at a much slower speed. So in the future, we could further evaluate the dynamic binding capacity of each column under their optimal conditions, and examine the arginine elution effect on 2 of the new resins we haven't got a chance to do, and then confirm the column performance using fresh harvest. So the take-home message is you got to choose your column based on the load condition and your process priorities. For example, if the whole cell DNA has already been effectively removed in the previous endonuclease and clarification step, so the number 2 and the number 7 columns can be sufficient and cost-effective. And with improved buffer formulation, so LVV stability has increased, making the longer processing time using the heparin resins more feasible. And although number 2 is a lot more expensive, but its impact on the overall manufacturing cost may be relatively small. As we all know, the plasmid procurement in the upstream production cost tend to dominate the process. With this, I deeply appreciate all my lovely colleagues and leaders from the PD and IND team who made a lot of great contributions to this project.